Welcome to Math 2318, Section 2.1. In question 1, we are asked to do some combinations of matrix operations. Maybe they're possible, maybe they're not. Let's see. In part 1 here, we have a plus 4b. Well, let's see. A is 2 by 3. 4b is also 2 by 3, so yes, with adding and subtracting, the matrices have to be exactly the same size. Other than that, we simply add up each of the components to get our answer. In the second part here, we have 2c minus 4e. Now let's see, 2c is 2 by 2 minus 4 times e. Well, 4 times e is 2 by 1. So I can only add and subtract if they are the same size. And in this case, they are not the same size. What about db? Well, let's see. d is 2 by 2. b is 2 by 3. The number of columns of D matches the number of rows of B. So yes, this is a valid operation to do. And so it's simply matrix multiplication. 4 times 8 is 32, plus 8 more, and we get 40. So similarly, you just get each of the elements by going rows of A times rows of D times columns of B. So that is defined. Let's see, what about E times B? E is 2 by 1, B is 2 by 3. Not possible. The number of columns of E does not match the number of rows of B. Let's see, in question 2, we have 2 times I2. I2 means it's a 2 by 2 matrix with ones down the main diagonal. So 2 times I2 looks like the following, minus A. Same size, so the operation is defined, and we simply subtract component by component. What about 2I2, which is here? Multiply that by matrix A. Yes, this is defined. I have a 2 by 2 multiplied by a 2 by 2. My answer would be 2 by 2. So 2 times 3 is 6 plus 0. 2 times 2 plus 0 is 4. 0 times 3 is 0 plus 10. 0 times 2 is 0 plus a negative 2. Let's see. In question 3, question about size. We have a product of A times B. We know that the resulting matrix is 8 by 4. Well, let's see. Matrix A is 8 by 2. I need a matrix B where the columns of B have to match the number of rows of A, so that has to be a 2. And since the product has 4 columns, that's the size of B, and so 2 by 4 is the size of B. In question 4, in general, matrix multiplication is not commutative. That is, A times B is more than not the same as B times A. In this case, they're asking us, is there a value of K so that we could make this operation true? Well, first off, you just find A times B. Okay, so here's A times B. We then calculate B times A, and let's look. Got a minus 2, got a minus 2. I've got 12 plus 2k and an 8. Minus 6 plus 2k is the same in both positions, so it doesn't make any difference what k is, that would match. Here I have a minus 8, here I have minus 12 minus 2k. And so if you look at these, they're actually the same. This is multiply through by minus 1. So we simply solve this one. So 2k is 8 minus 4. So minus 8 minus 12, which is minus 4. And so divide by 2, and I get k is minus 2. Alright, in this case, I want to find some matrix B where we would like A times B to be 0. And we want this to be non-zero, and we want them to be unique if possible. So I don't want the first column the same as the second column. So just a question of tracing this. So 2 times B11 minus 6 times B21 must be 0. And so you do this for all of the elements in our answer. So let's see, what does that mean? Well, if I group these two together and I look at my operations, all right, so here we've got this, and in this case I've got this. All right, so if I look at this, multiply through here by negative, it's the same as this. So I'm just going to use one of these equations, and I see that B11 is 3 times B21. And if I do the same for the other set of two equations, I get B12 is 3B22. So if I let B21 be 1, then B11 is 3. Now remember, we wanted the columns different, so I can't have 3, 1, 3, 1. So I let B22 be 2. 3 times 2 is 6. And that gives us matrix B, where A times that matrix gives me the 0 matrix. In question 6, we'd like to form the transpose. U with this capital T is U transpose. So what that means is I interchange rows and columns. So if here is U, here's U, I form U transpose. I take the column, make it into a row. It's multiplied by V, which is ABC. So I've got a 1 by 3 multiplied by a 3 by 1. The resulting answer is 1 by 1, which is just a regular real number. So now it's just minus 6a, 9b, minus 2c. I do the same thing for V transpose times U. So again, 1 by 3, 3 by 1, and I get the same answer. This is called the inner product or scalar product typically, which we will see later on. You'll also see this in physics or sometimes in calculus 3 called the dot product. All right. What about if I take U times V transpose? So here's U, here's V transpose. In this case, I've got a 3 by 1 multiplied by a 1 by 3, so the inside numbers match, and my solution will be 3 by 3. Similarly, if we take V times U transpose, the inside numbers match, giving us a resulting product that is 3 by 3. So I take the first row, which seems kind of strange, it's only one item, times the first column, again only one thing in it, so I get minus 6a. Again, this row, second column, this row, third column. Well, in reality, I just get a single product. Go to the second row, again multiplied by each of the columns. The third row times each of the columns, giving us our resulting product. And in our last problem, we'd like to prove that if I take the product A times B and I transpose that, it's the same as B transpose times A transpose. So to make life easier, first let's just consider that we've got A and B are 3 by 3, and we can look at them. So first off, they say the ijth entry in AB transpose is the jith entry of AB. Alright, so let's see. Supposing I consider A times B is C, and I look to see how would I get the C3, 2 element. Well, how do I get that? Well, let's see. It's the third row of A. Third row of A. So A31, A32, A33 times the second column in B. Second column in B is here. So I get B12, B22, B32. So the Cjth item, well, let's see, J was the row in A. All right, so each of these is a J, and then you go down the particular column in A. And so Cji would look like the following. And now we can extrapolate. What if our matrix A is n by n? Well, the sum would just get bigger, and in that case the number of columns and the number of rows just goes to n. Alright, so that's our solution for this part. What about the ith row of B transpose? Well, let's see. B transpose. Where would the ith row come from? The ith row would have come from the ith column in original matrix B. And the ith column looks like B 1i, 2i, 3i, all the way to ni. Well, what about the jth column of A transpose? Well, that had to have come from the jth row of A. So the jth row, here's my row number, and so that's A, J1, J2 up to Jn. So how do you form the ijth entry in this product? Well, if you look at that particular product, it would look like the following. And if you turn them around, because this is just multiplication of real numbers, so that is commutative, and what that shows you is that the ijth entry looks like the following, which matches what we got here for the answer to part 1. Therefore, the transpose of this product is equal to the transpose of each of the original matrices multiplied in reverse order.